Hey everyone, and welcome back to the channel. Have you ever wondered how we can look back in time and figure out just how massive an ancient volcanic eruption was? I mean, it's not like there were satellites or seismographs thousands of years ago. It sounds a bit like geological detective work, right? Well, today we're cracking the case of ancient super-eruptions, and our main clue is something called the Volcanic Explosivity Index, or VEI. Trust me, it's way cooler than it sounds. So what exactly is the VEI? Think of it like the Richter scale for earthquakes, but for volcanoes. It's a scale from 0 to 8 that helps scientists classify the power of an eruption. A VEI of 0 is super gentle, like the kind of eruption you see in Hawaii with those slow, mesmerizing lava flows. It's a beautiful, calm, and continuous eruption. A VEI-1 is a bit more dramatic, maybe tossing some rock 100 meters into the air. By the time you get to a VEI-2 or 3, like the eruption of Stromboli in Italy, you're talking about a significant event that can disrupt local life and air travel. These are the eruptions we often see in the news. But the scale is logarithmic, which is a fancy way of saying that each step up is 10 times more powerful than the last. So a VEI-3 isn't just a little bigger than a VEI-2, it's 10 times bigger in terms of the amount of material erupted. This means that when we get to the higher numbers, things get seriously epic. Mount St. Helens in 1980 was a VEI-5. It was a monumental event that completely reshaped the landscape. Then there's the famous eruption of Krakatoa in 1883, a VEI-6. The sound was heard thousands of miles away, and it triggered tsunamis and changed global weather patterns for years. Now here's where the detective work begins. How do we apply this scale to an eruption that happened, say, 74,000 years ago? We can't watch a recording of it. Instead, geologists become history's ultimate crime scene investigators. Their main piece of evidence is the volcanic deposit, the layers of ash and rock left behind by the eruption. Imagine a giant explosion that blasts a colossal cloud of ash, gas, and rock into the atmosphere. This is called a Plinian column, named after Pliny the Younger, who described the eruption of Vesuvius. This column can reach miles into the sky, even into the stratosphere. Once it's up there, winds can carry the fine ash all over the globe. Eventually, this ash settles back down to Earth, blanketing the land and the ocean floor in a thin, uniform layer. Geologists search for these layers. They drill ice cores in places like Antarctica and Greenland, where each layer of ice traps a sample of the atmosphere from that year, including any volcanic ash. They take sediment cores from the bottom of oceans and lakes. On land, they look for distinct layers of what's called tuff, which is basically consolidated volcanic ash. Finding the layer is the first step. The next is to figure out its volume. By identifying the same ash layer in multiple locations around the world, scientists can map out its total extent. They measure the thickness of the ash blanket in as many places as possible. The thicker the layer, and the wider its distribution, the more material was thrown out. Using this data, they can calculate the total volume of erupted material, or TFRA. This volume is a key factor in determining the VEI rating. For instance, a VEI-8, a mega-colossal eruption, has to have ejected more than 1,000 cubic kilometers of material. That's enough to bury the entire state of Texas ankle-deep in ash. But volume isn't the only clue. The height of the eruption column is another critical piece of the puzzle. How do they figure that out? It's all about particle size. The higher the eruption column, the farther the wind can carry the ash particles. Larger, heavier particles will fall out of the cloud closer to the volcano, while the finest, lightest particles can travel for thousands of miles. By analyzing the grain size of the ash at different distances from the source, geologists can model how high the plume must have been to allow for that distribution. A plume height of over 25 kilometers is a clear indicator of a very powerful, high VEI eruption. This is how we've been able to classify some of history's most mind-boggling events. Take the Toba super-eruption in Indonesia, about 74,000 years ago. Geologists found a massive layer of Toba ash spread all across the Indian Ocean, India, and Southeast Asia. The sheer volume of this deposit pointed to a VEI of 8. This was an eruption so powerful it likely triggered a volcanic winter, a decade-long global cooling event that some scientists believe created a bottleneck in human evolution. We're talking about an event that almost wiped us out. Another famous one is the eruption of Thera, now known as Santorini, around 1600 BC. Ash from this VEI 7 event has been found in Turkey, Egypt, and across the eastern Mediterranean. The eruption and the resulting tsunami are believed by many to be the source of the legend of Atlantis. By studying the ash deposits, we have been able to piece together the sheer scale of the cataclysm that befell the Minoan civilization. It's not just about satisfying our curiosity, though. Understanding the VEI of past eruptions is crucial for our future. By studying the frequency and power of these ancient events, we can better assess the risks we face today. Supervolcanoes, like the one sleeping beneath Yellowstone National Park, are still active. Yellowstone's last major eruption, 640,000 years ago, was a VEI 8. Studying the deposits from that event helps us understand what a future eruption might look like and how we could prepare for its global impact. This geological detective work allows us to read Earth's story, a story written in layers of rock and ash. The VEI scale is our Rosetta Stone, letting us translate those layers into a language of power and scale. It tells us not just that a volcano erupted, but how violently it did so, how it affected the planet, and how it shaped the course of life on Earth. It's a stark reminder that we live on a dynamic and incredibly powerful planet. The clues to its most dramatic moments are right there, buried just beneath our feet, waiting for us to uncover them. So the next time you see a picture of a volcano, remember the invisible scale that measures its fury. From a gentle lava flow to a planet-altering super-eruption, the VEI rating system helps us comprehend the immense forces that have shaped our world and continue to rumble beneath the surface. It is a powerful tool for decoding our planet's explosive past and preparing for its future. Thanks so much for hanging out and exploring this with me today. If you found this fascinating, make sure to hit that like button and subscribe for more deep dives into the amazing science of our world. Got any questions or ideas for another topic? Drop them in the comments below. Stay curious, and I'll see you in the next video.